Welcome to this third lecture video for Physics 10. We continue our study of kinematics in this lecture. In the last lecture, we covered the conceptual ideas in kinematics. This lecture covers the most math-heavy section of Chapter 1, Section 1.6, Motion Equations for Constant Acceleration. We start with the part 2 of chapter 1 overview. This part of the overview is very short as all the necessary details are covered in the separate lecture sections. In the second section, we look at the constant acceleration, motion, kinematics equations, making sense of different terms in the equations and ensuring that we don't get lost in the algebra. We use a couple different tools as we look at constant acceleration motions quantitatively to make sure that we make sense of the descriptions and results. In the lecture section, illustrating the scenarios showing non-zero acceleration with a zero velocity, we use a simulation software, AlgoDo, that you will see throughout our coverage of mechanics. And as you have been seeing some examples of motion graphs, both in the textbook and in these simulations, we set aside one section for a borrowed lecture from Physics 4a to explain these motion graphs. Finally, in the last section, you will see some homework help videos. Again, this is the most math-heavy section in the chapter and maybe even in the entire semester. So for the questions that require math/algebra, assistance is given both in the form of homework question hints and these homework help videos. With that, let's start with the chapter 1 overview, part 2. Hi, this is the overview video for Chapter 1, Kinematics, Part 2. In Part 1, we looked at the terms and concepts, the fundamental concepts, talking about position, velocity, and acceleration, distinguishing vectors and scalars. So in this second part, we are going to get a little more quantitative. We will look at the kinematics equations that's covered in section 1.6, and this is probably the most quantitative, most mathematical part of the chapter, and maybe even the entire semester. So there are some kinematics equations that you will see in section 1.6, and there are some homework questions where you will have to use this, and there's a ton of help provided. So if this mathematical material is giving you pause, this is probably the most amount of math that will be involved in the entire semester. So these kinematics equations involving constant acceleration is the entire subject of this lecture set that you will see. And in the next lecture set, we are going to be looking at 3 examples of motion. One is falling object or free fall. That's actually the most common example of motion under constant acceleration. And in separate video in the next lecture set, we'll talk about the definition of free fall, definition of projectile motion as one of the examples of 2D motion, and finally, the important features of the circular motion. There's a lot of overlap between free fall and projectile motion. In fact, free fall, you can think of it as an example of projectile motion where you don't have to worry about horizontal motion. They are both occurring under acceleration due to gravity alone. We are ignoring air resistance. And having handled the quantitative details in section 1.6, in sections 1.7, free fall, 1.8, projectile motion, 1.9, uniform circular motion, we are mainly looking at conceptual ideas. And in particular for projectile motion and uniform circular motion, you will have some simulations to play with to help build your intuition. So that's it for the part 2 of this overview for chapter 1. Please take a look at the lecture videos covering each of these topics in more detail. Thank you. So in last week's lectures, the last lecture, we covered the concepts and terminologies of kinematics. This week, we are going to get into a little bit more math of kinematics. In this lecture, we will cover what's sometimes called the kinematics equations. And not to worry, this is still conceptual physics. We are not going to do heavy into algebra. Your textbook does go into derivation of these formulas that we are going to talk about. And if you can read through those derivations and if they make sense to you, great. If that's challenging, I hope the summary here is useful. So I'll summarize. But before I go into the summary, I just wanted to point out the right-hand side of these infographics generated by Notebook LM. These 3 examples, applications of motion, we are going to look at them more in the next lecture. Still this week, but the next lecture we'll look at the falling object or free fall, projectile motion, which free fall is kind of a projectile motion, and centripetal acceleration, which involves things moving in a circle. So that will be in the next lecture. So other than just pointing this out briefly, I won't talk about that in this lecture, but look at the examples in the next lecture. I'll also have some simulation demos and some fun scenarios to look at, especially for projectile motion. Now, what we are going to focus more on in this lecture is the left-hand side of this infographic, the physics of motion or kinematics guide. Again, it's a Notebook LM generated. I've been playing with it this semester, and some of the things it produces are great. You know, I checked for typos, I didn't see anything. And so this is the summary of the kinematics equations that you will use in some of the homework questions, but again, this is still conceptual physics. We are going to keep the math as light as we can keep it. So these are the 3 main kinematics equations that you'll be working with in order to answer some of the questions in homework. And in the homework questions themselves, in the hint, I'll provide plenty of help with the algebra. And I have separate videos. That's a homework help video that will focus more on the actual homework questions. Here, I just want you to spend some time making sense of these equations. So sometimes people see these letters and get scared, and there's nothing scary here. Now, in this infographic, one of the things to watch out for as you look at equations like this, which your textbook also has, is to make sure that you know the meaning of these symbols. So in this infographic, they will actually spell out what each of these symbols mean. This is the final velocity. This is the initial velocity. This is the acceleration. And this is time. So you could actually, spell it out. If this process helps you do it, then you might write it out this way. Say that final velocity is equal to initial velocity plus acceleration times time. Now, as you can see, it takes a fair amount of space, which is really the reason we use these symbols. It's a single letter, usually 1 letter characters, variables. They represent a quantity. And when 2 letters are put together and they do mean 2 different quantities like acceleration and time, the missing symbol here, it stands for multiplication, basically. Here I wrote it out. So that's how you read these equations. Let me step through the other 2 equations and we'll make sense of those equations under some simplified situations. So this was the equation for the velocity. This is the equation for position. Again, the symbols are all listed here. This is the final position. This is the initial position. And there's some logic to how the symbols are labeled, how the subscripts are used to indicate different things. The next symbol is initial velocity, and the one after that is time again. And this is just fraction, 1/2, or you could write it as 0.5. Sometimes I do that in a calculator. Saves me a little bit of space. A is again acceleration, and T is time. And as much as possible, we try to use the same letter to mean the same thing. Later on in the semester, sometimes there's some overlap. At that time, I'll just start spelling things out so that they are not confusing. And the final equation is the same. I think there's no new symbols being introduced. V still stands for final velocity. V naught, V sub 0, still stands for initial velocity. 2 is 2. A stands for acceleration. And this combined quantity is the displacement. Oh, and these are the raising to power of 2 or squaring. You get those symbols in your calculator too. So hopefully all these symbols make sense. All those equations make sense. Now, here's something new I'm trying to do this semester. I'm gonna make the link to the notebook LM that I'm using for these materials available to the class. You can ask Gemini, basically, any questions you might have about this, anything that I didn't anticipate here. Okay, so I want you to talk a little bit about these equations, just making sense of, what they all mean. Because sometimes looking at these expressions with the multiple parameters, it can be a little bit intimidating if you haven't done math in a while. So I'm mainly going to be working with the first two equations here. This third and the last equation, sometimes we call this V squared formula. And it's most useful when you want to relate velocity, acceleration, and displacement without worrying about time. You can see here there's no symbol for time. So you'll be seeing this V squared formula in questions where you are interested about those quantities without worrying about time. But concept-wise, I don't think this is as useful right now. So I won't talk as much about this last equation. I'll focus on the first two equations. These are the core of the basic kinematics equations. Anything you need, if you're good enough in math, you can potentially derive them all from here. Now, these are equations for constant acceleration. So this A here is meant to be a constant, fixed value. If you're not dealing with a constant acceleration, then you shouldn't be using these equations. You need calculus to deal with a more general situation like that. We won't get into that again. This is conceptual physics. So keeping within constant acceleration, I want you to just make sure that this equation makes sense. Consider some scenarios. And I think the simplest scenario we can consider is, what if this acceleration is constant and it's constant at 0 value? Then the simplified expression we get, I hope it makes sense. If A is 0, then this second term, it's as if it's not even there in this first equation. And in the second equation, this third term, it's as if it's not even there if acceleration is 0. Then what the first equation says is acceleration, which is, remember from last lecture, it's a change of velocity per time. It's a rate of change of velocity. If this acceleration is 0, that means your velocity is not changing. So yeah, of course your final velocity is equal to your initial velocity. So the only thing the acceleration does in this equation is it changes your velocity over time. And if acceleration is 0, yeah, your velocity is constant also. And with a constant velocity, position equation becomes this simpler expression. And I can rearrange it a little bit to move x naught over to the left-hand side. I can do that by subtracting it from both sides. Then you get x minus x naught. That's your displacement, is equal to your initial velocity, which is same as your final velocity or velocity at any time times time. And this ties into what we talked about velocity in the last lecture. Velocity is the rate of change of position, or it's the change of position divided by duration of time. So this simpler version of the equation tells you how you can get your displacement from that rate of change times the duration of time. I hope this makes sense. This constant velocity, zero acceleration motion is probably the simplest, non-trivial example of motion we can get. And you are going to see this pop up in certain places. When we talk about projectile motion, the horizontal component of motion is constant velocity, zero acceleration motion. So having talked about what happens in this simpler, zero acceleration, constant velocity motion, I think we are now ready to talk about what happens if we have non-zero acceleration. Still constant. We still have to make sure that we are dealing with a constant acceleration. Otherwise, we can't use these equations. But what does non-zero constant acceleration do? In the first equation, it's, I think, easier to see. It's kind of comparable to what you just saw. The acceleration as this term. And I can imagine rewriting this the same way as before. Move v naught to the left-hand side. I can do that by subtracting v naught from both sides. Then I get v minus v naught on the left-hand side. That's equal to acceleration times time. Now, we don't have a word for this. It's not like a displacement. We don't have a special word for just the change of velocity. But this is the change of velocity. The change of velocity comes from the acceleration acting over some duration of time. So that's what this second term does. It changes your velocity over some amount of time. So if your t is equal to 0, then actually this whole thing is still 0. But over time, acceleration will introduce change of velocity. What the acceleration does in the second equation is a little bit it's harder to explain without calculus or without algebra. Your textbook will try to derive this expression using algebra, and it still takes a bit of a mathematical skill to follow. I encourage you to try, and if it doesn't make sense, don't worry. Again, conceptual physics. I think it's enough to say this. So when you look at the change position or change of position, let's say position. When you're looking at final position, it's got three parts that contribute to it. There's initial position where you're starting from. That'll be your starting place. And you have your change of position that you can attribute to simply the initial velocity. If nothing else happened, initial velocity acting over some amount of time will cause the position to change. So far, so good. Now, what acceleration does is it introduces a third term. It introduces this that causes additional change of position. This additional change of position, it has this coefficient that you have to remember, 1/2 times acceleration times, now it depends on time, and it goes as time squared. And if you want to see exactly where that factor of 1/2 and the square comes from, you can look at the derivation in the textbook. I can probably point this out still at a conceptual level. So when you look at position, the unit of position is in meters, in SI units. And every single term you can see here has unit of meters. Your initial position, of course, has unit of meters. And this term here, it's a velocity times time. Velocity comes in unit of meters per second. Time comes in unit of second. So these two quantities, seconds, cancel out, and you have unit of meter. And in this last term, when you look at the units, 1/2 has no units. Now the acceleration, let me write it over here so there's more space. Acceleration comes in units of meter per second squared. That's what you saw in the last lecture. That times the time squared. So second squared. So this squared thing, it helps make units come out correctly. Second squared cancels out the second squared from the acceleration, and you end with the unit of meter. So in this entire equation, every single term that you are adding together has unit of meter, and everything is dimensionally consistent. So that's the summary overview of these kinematics equations. Again, you have some homework questions where you will be using these, and I provide a lot of algebra help with those. You will see some of those homework help videos in this lecture set that I'm putting together. And this is probably the most mathematical part of the class. Again, this is conceptual physics. We try to keep the level of math that proportionalities as much as possible. It's just in a couple kinematics questions where you do need to work a little bit with algebra. Again, I'll give you a ton of help as you are looking at those slightly more mathematical portion of the class than the rest of the semester is gonna be. So that's the kinematics. This is what Notebook LM keeps calling kinematics toolkit. I hope that's helpful. If any of the generative AI stuff isn't helpful, let me know. This is my first time using AI in teaching physics, so I can dial it back, dial it up, whatever is more helpful to your learning physics. Thank you. So in this and the next lecture section, we are going to look at some graphical tools that will help us visualize the mathematics of one-dimensional motion. You will see some simulation and motion graphs. This particular video comes from one of the homework help sessions where I was explaining the scenario of having zero velocity with non-zero acceleration. Please give it a watch. So if I submit this, I'll get 0 score because I have basically selected every single wrong answer and none of the correct answers. And if I select everything, then I also get some credit for having selected the correct choices. Anyways, so with all that technical detail behind the scoring aside, so your goal with a question like this is to get 100%, which if you're just guessing randomly, it will take you many tries because unless you understand what's going on, it might have taken you many tries to get that this is correct choice and that this is correct choice. So that's what's going to give you full credit. Now, so suppose you know that that's the answer, that this is correct and this is correct. As in, when you have a car starting up from rest, then the velocity is 0 at that moment in time, but the acceleration is not 0. And a ball that is thrown directly upward at the top of its trajectory also matches that condition, and none of the other choices match the condition. And so, once you get to this point, then you know what the correct answer is. And, that's good. That's good for you to know. But what I want you to get more at is to understand why these two are correct. And I think it's easier to understand why the other ones are not correct. So why these two are correct. So a ball that is thrown directly upward at the top of its trajectory, that is a little bit easier. Let me actually demonstrate this with a simulation. So this is a simulation. I think you've seen me using other contexts for this class. I have recorded the videos where I use this simulation. So when I have something like this, then so this is how I can set up a ball that is thrown directly upward. I can set up an initial condition for this ball. I can give it an initial velocity. So directly upward means I'm giving the ball a y velocity, a positive, let's say, velocity of +7, and no x component of velocity. So when I let the simulation run, the ball will go directly upward, and then we'll see what happens. Let the simulation run. Okay, so that's kind of what it looks like. And so let me slow down the simulation a little bit so that I have time to stop it
at the moment when the choice is describing. So I think this is something that people need a training to learn to think in this way. Is um, when you look at a motion like this, it's kind of easy to think about the entire motion as a whole. You threw a ball up, it went up, and it came down. All right. Now, the thing that needs training to break down and think it through in very clear detail is trying to think of this as something that as some sort of a change that happens over time. So you can talk about what a snapshot, what is going on at one moment in time. So at this moment in time, t equals 0. This ball has a velocity of 7 meters per second. That's kind of how I set it up. And when I let it run, as it's moving up, now it has moved up, it still has some velocity. It's changed. I didn't change it. The simulation changed it. Simulation changed it because the simulation includes this gravitational acceleration. That's why it's changing. So when this is at the very top, there is where it has zero velocity or close to zero velocity, but it still has a downward acceleration. I wonder if I can kind of illustrate that. Um, let's see, velocities, visualize. I don't know if I can visualize the acceleration. That might not be something I can actually visualize. Is there other? Yeah. Um, so yeah, there isn't really. Um, so I think this is what I can do. I can draw a plot, and in a more mathematical physics class, this is how we would do this. We would do or we would use a graph to represent this quantitative information, because that's really what people need training in thinking quantitatively about something that you can also approach it qualitatively, but qualitative approach sometimes misleads you. So when I plot this, so right now it's plotting time and speed. Let me just plot that and see what I get. So it starts out with some speed here, 7 meters per second. Okay, it's slowing down as it goes up. And at the very top, oh, I see. It kind of looks like it's bouncing off of zero. And then it's speeding up again until it comes back down to the same-ish speed that it started out at. All right. So I guess that's what we are referring to here then. Here, 0 at the top, that it has a 0 speed. I mean, you can see it and it's kind of intuitive that, yeah, that's at the very top, you have 0 speed. The second part, that it has non-zero acceleration, takes a little more thinking through. I guess you could kind of take it as a given. It's in a gravitational field, so it always has downward acceleration. You could accept it that way. I think a better way to look at it is to graph something slightly different, not speed, but velocity with positive and negative values. So let me make this a y component of velocity. Yeah, and so I guess I'll show gravity field too. And let me just let it run and see what happens. As it goes up, it's slowing down. And when it's at the very top and reaches a zero velocity, it doesn't stay at zero velocity. And in fact, so now the later part, so this is what I hope you find interesting. At this moment where it reaches zero velocity, with the speed, this graph suddenly changed the direction. But when you graph a velocity, it doesn't do that. It's changing in the exact same way it was changing before. And now as it moves down, so it's speeding up. But what speeding up here means is that velocity is getting more and more negative. So at this moment in time, when the ball was at zero velocity, its acceleration is not zero. the information that you see in the screen there, dy dx is kind of telling you about the slope of this curve. That at that point, yeah, slope is not zero. It's minus 9.75, or close to this 9.8 meters per second squared, the gravitational field. Um, so that example, I think once you kind of think it through, it's easy to understand. Partly because there's multiple ways to understand it. Now, the other example is, I think, one that I get more questions about, which is this one: a car starting up from rest. Because then, I guess. I think there are different places where you could have questions on, as in a car starting up. So since it's moving, then that means the velocity is not zero, isn't it? That's one way you might ask a question. Or the other is, it says rest, so it's not moving, so acceleration is zero too, isn't it? So having asked both of those strawman questions, let me set up this simulation to help to kind of demonstrate how that particular scenario satisfies both of the described conditions. One, that velocity is zero. Two, that acceleration is also non-zero. So I need to set this up. Let's see. Um, and instead of a car, I'm just going to have a block. Block is easier. Let me just let the simulation run for a bit so that it's resting. Um, I think I can let it run faster. If I'll just do a slow acceleration. So let me pause the simulation while I make changes. So these are some of the changes I'm gonna make. I'm going to make it frictionless. It just makes things easier. Um, and I need to add a thruster. The thruster is going to give me a way to apply a constant acceleration. So there will be some force. I think that's going to be fine. And let me just try. Oh wait, is there a way to toggle activation key? Yeah, let me choose an activation key. Um, S for start, and so that'll toggle. So if I let it run, okay, yeah, and when I press S, it starts. Okay, good. Um, all right, so I think I'm all set up. Let me show the velocity plot so that I'll have something quantitative to talk about this over. So here's the velocity plot, and let me make it a velocity plot. Here, it's not too relevant, but let me make it a plot of the horizontal velocity. So, okay, I'm going to let the simulation run for a bit. And then after waiting a second or so, I'm going to let it accelerate. And after waiting for another second or so, I'm going to stop the acceleration, but let the simulation continue running. And then eventually I'm going to stop everything. Okay, so simulation is running, acceleration starts, and then no acceleration, and then stop the simulation. Yeah, and my block went off to the right. You can find it later. Um, maybe let me redo this. I'm gonna make the force smaller. 1 Newton. Okay. Let me redo it. Toggle, and then stop, and then stop the whole thing. All right, so this is the quantitative description of the entire motion. And this is where quantitative description is useful. It helps you divide the motion into different parts. So, when we talk about a car starting from rest, it's easy to be misled by different parts of the motion. A car starting up from rest. You could be misled by the rest part. You could be misled by starting a part. Let me point out all those in this motion graph of the position, or sorry, of the velocity versus time. So for this part where the car was at rest, your velocity is zero. Good. And your acceleration is also zero. As in, velocity remains at zero, the slope is zero, so acceleration is zero. Now, that's the kind of from rest part. And in this part of the graph, you are seeing the motion. Here, velocity is not zero. Velocity is increasing, increasing, increasing. So acceleration is also not zero. So this is the kind of moving part. Now, the challenging thing about that particular scenario is you really have to think about a single moment in time. And that single moment in time is this moment here, where it's just starting. Now, where it's just starting, your velocity is still zero. Or at where I have the cursor, you see 0.006 meter per second. You can imagine me positioning it so correctly that it'll be exactly at zero. So your velocity is zero, you're at rest. Now, you see that line there, that line indicates the slope. The slope is not zero. Your velocity is changing. That's why your velocity is changing away from zero as time goes. So when you imagine this particular moment in time, where the car is just starting up, that's where your velocity is still zero, but the acceleration is not. So, yeah, it it is a bit of a tricky question in that when you think about it quantitatively like this, then it's easier to make sense of it. Kind of let math help guide you. But this is the challenge with the conceptual physics. Physics is frankly easier to describe with all the math. So when you don't have the math, then it's hard. So.
This video that you will watch is what I recorded for my Physics 4A, the calculus-based general physics class. That's why you will hear mention of calculus once or twice. But this video on motion graphs is mostly conceptual, and the tool that I'm demonstrating here is the graphical problem solving tool. So there isn't much algebra or math involved here. When you hear me say the word derivative, just know that it's referring to the slope of a graph. So I thought the content of this video will still be useful for you, the students in conceptual physics. So I'm including it in this set of lecture videos. Let me know of any questions in any of the parts. I hope this helps illustrate the plot of position, velocity, and acceleration that you have seen in other lectures in the textbook. And I hope this longer video explicitly explaining the motion graphs with some examples is helpful. Please give it a watch.
So I have three axes to draw position, velocity, and acceleration for different scenarios. So I wanted to just to talk about some of those scenarios and represent those scenarios in terms of motion graphs. So I guess we have maybe about 10 more minutes on this. So let me do one that kind of relates to one of the questions, homework questions you have. But I realized in the homework question, it's kind of cut a little bit short. So I will extend that a little bit to illustrate that with a situation where you might have to describe some situation with multiple stages. So the homework question I'm thinking of, it has a scenario with a diver diving from uh, 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 diving board. I think I'm saying diving too many times, but it's okay. So the situation will describe it. A diver jumps straight upward from a diving board with some speed v naught, and on the way down, she barely misses the diving board and um, dives straight into the pool. And I think your homework question ends here, but let me add a little bit more bit so that I have more interesting motion graph to sketch into the pool. And after entering the water, she slows down with an acceleration. Let me make up some number of a equals 3g, or that would be approximately 30 meter per second squared. Um, so that's the scenario, and I want you to show you how you would sketch something like that on a motion graph if you had to. Now, one thing I will start by saying is something like this is very difficult to sketch on position graph correctly at a first try, because your intuition kind of messes you up. So let me give you some attempt, and then I will use the velocity and acceleration graphs to make some of the more ambiguous things clearer. So let me draw a kind of reference line for the water level, so that at least I know when the diver enters the water or not. So wait, is that the yeah, water level? So let me draw two levels. There's one level for the water level, and I think I need a second level for the where the diving board is. So let's say the diving board is around here. Then on a position graph, you might draw something that looks like this. The diver starts from the position of the diving board at time equals 0. And maybe you remember enough of projectile motion or motion with a constant acceleration that you know to draw something that looks like a parabola. So this is with acceleration being downward acceleration of minus g. And then what's a little bit harder to do on a position graph is what happens to the position after the diver enters the water. You have some sense that the diver should come to a stop because it's something about slowing down. And that's kind of where you have to leave it. And this graph as drawn, it's ambiguous. It's not wrong, but there are some features here that's not best represented on a position graph. So let me do that on an acceleration graph instead. So on an acceleration graph, I can translate the physical situation described in this statement a lot more faithfully, because I can take a point that represents when the diver enters water, and that's a very clear dividing line for acceleration. So before the diver enters water, I know that the acceleration of the diver should be minus g. So this is minus g. And while the diver is in the air, the entire time, the acceleration is minus g. That's what free fall, motion under gravity alone is. And when the diver enters water, then the acceleration changes. And this is where you kind of have to think through carefully whether it should be minus 3g or it should be plus 3g. This is where you want to think in terms of relative directions. The diver, at the moment when she enters water, she's moving downward. So in order for her to slow down, the acceleration must be upward. And you can kind of see that represented here in the upward curving position curve. And it's in this acceleration graph that you would make that clear, that after diver enters water, she undergoes an upward acceleration of plus 3g. So yeah, on the acceleration graph, this and this is where I should stop. And on the acceleration graph, this is more or less one-to-one faithful representation of what the questions take, what the word description described. And for that reason, when I usually draw a motion graph, it's the acceleration graph that I usually want to start out with. So, okay, once you have acceleration graph, then you have enough information to start drawing velocity graph. And this is where you have to put on your analytical hat and really think through this mathematically. I know it all looks like a picture, so that's where people sometimes make a mistake of kind of going going with your feelings. And until you develop your intuition for kinematics, you don't want to go with your feeling here. You want to actually read carefully from what the statement says, keep thinking about what you learned in calculus, and apply that here. So it said diver jumps straight upward with some speed v naught. So you are given an initial velocity, and you need to use that here. You cannot start the velocity from zero position or any random point you pick. There's a positive v naught that you start from, and it's positive because it's upward. And then so I like to think linearly, sequentially in time. So I know what the value of velocity at time equals zero. So the next question is, how is the velocity going to be changing as you move on from time equals zero? And the one guide you have is the acceleration, which is the derivative of velocity. So it's going to give you the slope of the velocity as you go from here. You have minus g, so that should be the slope, something downward sloping, negatively sloping. And I'm trying to kind of put the negative slope in a way so that it'll make my graph kind of to scale for the next part. So let me do that, and until I reach this point in time, when the diver enters water, it's going to be this one constant slope the entire time. So the graph will look something like this. And so this point is a special point that you couldn't see in the acceleration curve. It doesn't look special in the acceleration curve, but it's this special point in the position curve. It's the point where the diver was at the top of her motion. So that should match up in your position curve, where you do see now that the slope of the position curve is zero, and the value of velocity is zero there. And at the moment where diver enters water, something happens, and that something is that the slope of this curve now changes to positive 3g. So it's going to go from being um, negatively sloped, downward sloped, to upward sloped, positively sloped, and it should be steeper than this because because now it's 3g. So let me just put this point here so that I can do it reasonably to scale. So it looks something like this. So once again, constant slope, and this should the slope here should match up with the value you see here. The slope that you see here should match with the value that you see here. So and once you draw this correctly, then you can see that how I drew the position curve here matches up. I started out with some steep negative slope, and it flattens out to a zero value or zero flat slope, and that matches with the velocity going to zero. So that's an illustration of drawing a motion graph. Okay, let me do one fun one. So I guess I had a bunch of scenarios. I don't have time for all those scenarios. So let me just do one, what I'm going to claim is a fun one. So this diver thing, it's good for illustrating how you go about drawing the motion graphs for a very clinical kind of physics problem type question. But it's not, for most of us, it's not very relevant to what you might see every day. So I wanted to illustrate a motion graph for what you might call stop and go traffic motion. That might be something that people see more regularly, like if you're driving in a congested city traffic, you are able to move for a bit, then you have to stop, move for a bit, and then stop, move for a bit, and then stop. So I hope that description is clear enough to people So motion of a car in a congested traffic condition. So let me do that. And this is actually a bit of a, it's kind of opposite of the scenario I just drew. It's actually easier to draw with a position graph because I think you can intuitively get what that motion should look like. So let's say time equals 0, you start up from position 0. So you start by moving and then you stop for a while and then you are able to go again. So you start moving again and then you stop for a while and then you are able to move again and then stop for a while, able to move again, stop for a while, and so on. It looks like this. And I could have drawn it more prettily, but that's a kind of, and intuitively that actually describes what a stop and go traffic looks like. And once you have that, then what I want to do is draw what the velocity and the acceleration curve looks like. There are some idealizations I'm making here. So for these segments of motion here, I'm going to assume that it's moving at a constant velocity. In real life, it might not be, but I'm just getting, I guess, the average velocity and approximating that to be the instantaneous velocity for the entire time, even though it probably isn't. So let me get a few time marks here. So I will get those into the velocity curve so that I plan out my time axis correctly and I don't run out of any space as I'm drawing them. So I have, it probably works out best if I number them. 1, 2, 3, 4, 5, 6, 7, 8, 9. I shouldn't have done so many. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And I'll probably need that for acceleration too, so let me do that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So so the time period is broken up into basically 9 or 10 periods, depending on how you count. And I'm just gonna sketch out what velocity and acceleration looks like at those different times. So from 0 to 1, I have constant positive velocity. So this is the velocity from 0 to 1. And then I have constant but 0 velocity. So that's 1 to 2. And then I have constant velocity, which I guess I drew it faster than the first one for some reason. And then it's 0 again. And then it's some positive constant value. And then it's 0, 5 to 6. And then 6 to 7, it's some positive value again. 7 to 8, it's 0 again. And 8 to 9, it's some positive value again. And then 9 to, it's 0 again. It looks very disjointed. And it's part of the approximation that I'm making, because I'm making this approximation that velocity is suddenly changing from one value to 0. And within that approximation, the velocity looks disjointed. If you want that to look more real, you could connect them, and that looks more physically meaningful. It looks like a more physically meaningful velocity curve, but it's a part of making that approximation of that there's a sudden changes. And you will see that approximation bleed through in the acceleration curve as I draw it now. So in the acceleration, when I draw the acceleration curve, it's almost better ignoring the position curve altogether, because really the relationship that's most useful in giving you the intuition for acceleration is that it's a derivative of the velocity, meaning it's represented by slope of the velocity curve as a function of time. And sometimes that'll make us draw something that initially doesn't look intuitively correct, but well, that is what's actually mathematically correct. So from 0 to 1, where the car is moving with a constant velocity, the acceleration is 0. And a lot of people might have difficulty with this initially because it's moving. Why is acceleration 0? Well, the slope here is flat. Velocity isn't changing. Now, to get to this positive velocity, you probably had a non-zero acceleration before, but during this period, 0 to 1, acceleration is 0. And I guess maybe let me do this all the segments right now and get it out of the way. You see that for all the segments between 1 to 2, 2 to 3, 3 to 4, they are all flat. That's a part of the approximation I made. So acceleration during all these periods within this approximation is all 0 between these transitions. So that's the part that, oops, it's meant to be 0. That's the part that's going to be look very unintuitive to people who haven't thought about this way before. That for vast majority of the time, acceleration is 0 because you have constant velocity. Whether it's at a constant non-zero value or whether it's at 0 value, it's constant. So acceleration is 0 during those times. What gives you all this interesting motion in the end is what happens at a very small moment of time. So over this very small duration of time, you have a highly negative acceleration. So I have a spike in acceleration in the negative direction here. I have a spike in the acceleration in the positive direction here. So this acceleration curve is very poorly behaved, which is why it's not a good one for practicing how you draw the motion graphs. But basically, these very steep slopes are what gives you these pulses in acceleration. Positive pulse, negative pulse, positive pulse, and negative pulse. And it looks very it doesn't look correct according to intuition of many people starting up, but this is what the math says it is. And part of your experience with learning kinematics, the way we cover actually in calculus and in physics, is developing this intuition that this very oddly looking graph, which you might not have expected, is actually correct. And if you have experience driving, it kind of does match up with your driving experience, hopefully. Well, at least a very bad driver. When the car comes to a stop, you weren't planning, so you suddenly come to a stop, sudden braking, and then when the car in front of you starts get going, you suddenly accelerate, and then when it stops, you suddenly stop. I mean, it does represent a very bad driving. But if we are trying to draw a very good driving, then these position curves wouldn't look like a straight lines. They would look like a parabola, where acceleration is more gentle.
In this section, you will see some homework help videos for the questions in the first half, 2/3 of the textbook. By the way, in these videos, the section numbers and the chapter numbers are different because they are the old numbering from when our textbook used to be hosted on OpenStax CNX platform. When it was ported over to LibreText, the chapter numbers shifted by 1. Chapter 1 became chapter 0. What you see as chapter 2 here became our chapter 1 currently. And the section numbers shifted as well. The introductory section that used to be not numbered at all became section 1, and all the remaining sections got shifted by 1. So just to watch out for the mismatch in the section and the chapter numbers. The content should help out with the calculations and demonstrate some of the techniques that you may need to use on some of the more quantitative math-heavy questions, the most math-heavy question of the entire semester in this homework set. With that, here are the videos. I have 3 recorded in the format that you will see here, and 1 additional one from past virtual class session in a slightly different style. So this is a question dealing with free fall. It says if your reaction time is some number of seconds, in that amount of time, how far does an object drop? Now, there are hints and there are relevant chapter sections that would help you as you are trying to think through how to do this question mathematically. So in the hint, it said that the example calculating distance traveled under constant acceleration, dragsters would be the example that's relevant. And if you look at it, here it is, dragsters. It is mathematically very analogous, and what that means is both the motion of an object being dropped from rest and the motion of this car accelerating from rest are mathematically very similar. So this textbook example goes through it, gives you some equations that you would use, and if after reading through this example, if this example makes sense, then you can probably do the problem okay also. There's a little bit of shift in thinking. Instead of being horizontal acceleration, it's a vertical acceleration. But I think most people can handle that. So the rest of the video is really for people for whom this example doesn't quite make sense, because to tell you the truth, this example was drawn from a textbook that requires trigonometry, and our class is meant to be conceptual physics. It's not meant to require large amount of algebra and calculations. So let me try to make some sense of this. So what this equation says here, it comes down to saying this. Let me rewrite a slightly changed version of this. And we can make a little sense of it, expressing it this way. So I'm going to put this x naught with x to write it x minus x naught equal to the rest of what's on the right hand side. V naught times time plus 1/2 times acceleration times time squared. And really what this means is, in plain language, this is the distance traveled, and that's equal to speed times the duration of time. And you might remember something like this from constant speed motion. So with there being acceleration, what changes is now you have this second term. So it's plus 1/2 acceleration times time squared. And one more thing that changes, this speed is the initial speed, what the object starts out moving at. So for the situation like one described in this example and in the homework question, your initial speed is 0, which is why you only end up with this 1/2 acceleration times duration of time squared, and the textbook is giving you this equation. All right, so this might make some sense. Let me give you one more example to try to help draw out your intuition for a falling object like this. So this is a simulation where I can show you the familiar falling motions that you will recognize from everyday life, and also make some measurements that we are not used to making in everyday life. So I have a ball at some height, and when I hit play, it's going to fall. Hopefully this feels reasonable enough. It feels natural enough. All right, so let me go back. And just to do it one more time, in case you missed it the first time. So that's the falling motion. Now, this time I'm going to be a bit more careful and actually measure how long it'll take to fall through this height. And I'm going to do it by this stopwatch here. And I'm going to be very careful to try to stop the simulation the moment the ball hits the ground. So ready, set, go. All right. So about 1.3 seconds is how long it took for the ball to fall from the height that it fell from. Let's try moving the ball a little bit to half the height. Then how long do you think it'll take to fall now? Half the time it took before. So before it was 1.3 seconds. So something like 0.65 seconds. Let's give it a try. It's almost 1 second. Let me do it one more time. Yeah, almost 1 second. So for the ball to fall through half the height it fell through originally, it doesn't take half the amount of time, it takes a little bit more than half. In fact, in order for it to take exactly half the amount of time, it'll need to fall through a quarter of the distance that it originally fell through. Let me give it a demonstration. There, about 0.65 seconds. Let me try one more time. Yeah, about 0.6, 0.7 seconds. So this is the demonstration of that formula you have seen. So going back to the formula, this is the expression that you have seen before. And what I was demonstrating was that when the distance changes by a factor of 2, is reduced by a factor of 2, the time doesn't reduce by a factor of 2. In fact, in order for time to reduce by a factor of 2, then you have 1/2 squared. So the distance is reduced by a factor of 1/4, 1 over 2 squared or 4. And that's what the demonstration was showing, that for the falling time of the ball to be half the amount of time before, the distance has to be a quarter of the distance it was before. And if you turn on some additional visual display here, you can kind of see why. Let me turn on the velocity indicator. Then as it falls, watch what you see. One more time, maybe a little bit slower. Let me do it in half time. So initially it starts with a 0 velocity, and as it accelerates downward, the velocity increases up until the moment when it hits the ground, then much messier things happen. So this is the motion under constant acceleration, motion in which velocity is constantly changing. And the kinematic formulas that describe this motion is slightly more complicated, which is the reason for these formulas here. This formula covers the most general case, especially your object might have any initial velocity. For the question we are looking at the simpler case of 0 initial speed. So it simplifies down to this expression. And for the purpose of the question, really all you have to do is plug in the numbers. The acceleration is the gravitational acceleration, 10 meters per second squared. And you are given the time in seconds. Plug those in, you get the answer in meters. Oh, so I guess that means you have to convert your meter answer into centimeter. So that's it. I hope it makes sense. If not, please ask your questions and we'll see what we can do. Hi, this is the second of the 3 videos on the 3 homework questions on falling objects. And when you look at this question, it might look like it's not exactly describing a falling object. It's describing a rock that's thrown upward. But we still call this falling object because throughout its entire motion, it is accelerating downward. So we say it's in free fall while it's in its entire motion. So this question also has hints that link to specific textbook sections with the specific examples, but you do have to do a little more work to connect from the example to the question that you are actually solving. So let me go down to the example. The example being referred to is calculating position and velocity of a falling object, a rock thrown upward. And this example is useful for the graphs. Read through it, and it has these graphs of the positions, velocity, and time. And what you can see here is when the rock is at the top of its motion, at that point is when the velocity is zero. You can understand it as rock is neither going up nor down, so it's very momentarily at rest, so its velocity is at zero. So once you have that, then you do need to go back to the kinematics equations you have seen up here. So you have seen these kinematics equations for objects in free fall. This describes how the velocity is changing with the acceleration of minus g, and you have this position and other things. I want to focus on this velocity equation. So what we are saying is at the top of the motion, the velocity of the free falling object is zero. So this equation becomes 0 is equal to your initial velocity minus g, gravitational acceleration, times time. So solving this for time, you can get the amount of time it takes for the rock to reach the top of its motion. So this is probably an equation you want to write down so that as you're doing that homework question, you have it handy for reference. Let me show you the simulation to help you develop your intuition and also to help us answer part B with a little bit of a shortcut. So this is the same simulation we used to before, but instead of dropping the ball, we want to give it a little initial velocity upward. I think the problem gives a larger velocity than that, but let me just do it at 25 meters per second. Then when I run the simulation, oops, that's too fast. Let me zoom out. All right, that seems better. I think I can zoom in a little more. And let me scale this stopwatch. And give this ball upward velocity again. And let's give it a try. Alright, that seems reasonable. That seems intuitively what you would expect to see in a ball you throw upward. So this time, let me actually try to measure how long it will take to reach the very top of its motion. And stop. Yeah, 2.5 seconds. And you can verify this with the formula that you wrote down. So g, gravitational acceleration, is approximately 10 meters per second squared. I gave it an initial velocity of upward 25 meters per second. And when you divide 25 meters per second by g, 10 meters per second squared, you get 2.5 seconds. So what we see here is what you would calculate based on that formula that you saw on the previous screen. Alright, so this is all very exciting. And the reason I set up that simulation was to help us answer this question. What maximum height does the rock reach? Now, technically, yes, you can use these kinematic equations and you can use the y height. Now you know the time, plug those in. So you can actually do that, and if you feel comfortable doing that, then please do. Let me show you a little shortcut. And the shortcut is based on this idea. When you look at this motion of the ball, there's a symmetry to it. How long it takes to go up, how long it takes to come down. It seems like it's a mirrored version of each other. How long it takes to go up, how long it takes to go down. So instead of thinking of this like a ball that's thrown up, we can think of it like this motion. A ball that's starting from here at rest and is being dropped. And because of that symmetry, you are going to know how long it's going to take for this ball to drop down to ground. 2.5 seconds or whatever you calculated with your number. Then given that time, In a previous question, we had this much simpler formula. Distance traveled is 1/2 times acceleration times time squared. You can just plug in the time into that formula. Understanding that you are not answering the exact question that your problem asked for, but knowing that the numerical answer that you get for this motion here is the exact same numerical answer that you get for the first half of the motion. So as long as you're clear on that, then this shortcut is fine. It makes for an easier calculation. If you have any questions, please ask me. And we'll look at the third example of not falling object, but an object under constant acceleration. Hi, this is the third and the last homework help video on constant acceleration motion. So this is the question we are looking at. A car moving at some speed initially and comes to a sudden stop, accelerating at a given rate. This is what some people might call negative acceleration. And like with other homework questions so far, there's a hint. And there's an example in the textbook that is a very close match to this question. So in section 2.5, if you scroll down to almost the end, is where the example calculating displacement, how far does a car go when coming to a halt? And it's the exact question. And this can be a difficult question. It uses something called the PHYS squared formula. It's one of the kinematics equations. And I'd say for this homework question, use this formula to do it. You are given the initial velocity v naught. Your final velocity v is 0. And the acceleration, you are given that you should use a negative version of the number. And that indicates that your acceleration is in the opposite direction to the displacement. And you'd be solving for the displacement, x minus x naught. The example actually does work through that, so you can follow that. And this is the formula where you plug in the numbers. So I want you to use the remainder of this video showing you simulation of this situation, because so you can use the results here. All the equations, formulas are here. But what I'm most concerned with is if this scenario makes physically intuitive sense. So let's look at some simulation. Alright, so in this simulation, I created this 1 kilogram block. It will move frictionlessly along this surface. So let me give it a little bit of an initial velocity. Let's say 9 meters per second. And if I just let it go, then it'll just move at a constant speed. So I need to attach a thruster here so that something will push it back. It's a 1 kilogram block, so I'll need to apply 10 Newton of force to produce acceleration of 10 meters per second squared. That's next week's material. For now, trust me that this will produce a 10 meter per second squared acceleration. So now, when I let the simulation run, alright, so this is slightly different from what's given in the question, because it's not just coming to a stop. After eventually coming to a stop, it'll accelerate the other way. It's like a rocket car applying reverse thrusters or something. So let me build a parallel version of this so that we can compare them, and we can see that at least up to the moment it comes to a stop, there's no distinction between them. Alright, so the second floor setup has been set up. So it's the same block, 1 kilogram block, and what's different with this block is it has a friction coefficient of 1. That's also next week's material. So what you have to know about this block is that it now has friction with the ground under it. And the frictional force will produce an acceleration of 10 meters per second squared. Now, when you let this simulation run, this is what you see. So with the reverse thruster, once the block comes to a stop, Then the acceleration continues, eventually speeding up the block in the other direction. With the friction, once the block comes to a stop, then it remains at a stop. So what the question is describing is more like the upstairs version, but the both version is acceptable for what we are looking at here. So this is what I want you to highlight. This is the starting point for both blocks, and this is how far it travels before coming to a stop. And let me display the velocity information so that you can see intuitive picture of this. So when we let the simulation run, over time, velocity decreases to 0. And what the question is asking for is this distance here, from the starting point to the ending point. And the v-squared formula that you see in the example relates this distance to the acceleration without needing to refer directly to the amount of time it takes to go from here to here. So I hope that makes sense. If there are any questions, please ask me. Until next time, bye.
Okay, so these two questions are, I guess, a little bit of calculation. So this one, this is actually technically a review of the other question that was another reaction time one. But I think the reason I was giving you more hint here is you do need to do a little bit of algebra. So, so I did do the algebra here for you because once again, different people come from different places. For some people, some of you who have been out of school for a while, haven't done math in a long time, this whole taking square root, that's unfamiliar. That's why I've done it. Now, you should know how to do the square root in your scientific calculator. So even on Windows, this Windows operating system calculator, it can do square root. This is the square root symbol, and you press that, it does a square root of the number that you have in the window. So square root of 4 was easy, 2, square root of 7, some irrational number. So yeah. So let me do question 6. And because question 6 has more mathematical expression, so let me just walk you through how you are supposed to use this to answer this question. And the other part that makes this question a little bit challenging is that it's kind of a less numerical. I don't exactly give you the numbers to plug in, but maybe I can give you a bit of a trick that you can use to make your numbers simpler, or make it conceptually simpler by using numbers. So this is what the question is. The severity of a fall depends on your speed when you strike the ground, all factors but the acceleration due to gravity being the same. How many times higher could a safe fall on the moon be than on Earth? That is, given that gravitational acceleration on the moon is about 1/6 that of the Earth, if you could jump safely down from a meter height on the Earth. Okay, so I'm just going to say that is a safe height. And from how high a height in meters could you jump down from on the moon without risking injury? So I'm just going to take this one thing from the hint. Hint has you reviewing this, and it refers you specifically to the v-squared formula. So, and it simplifies it down to this. So let me just use that, and that'll help me. So I can use numbers to kind of simplify the conceptual part. So the problem just gives you information. Let's say 1 meter height is safe to fall down from on Earth. So, okay, since the question claimed the severity of a fall depends on your speed when you strike the ground, let's calculate that. I'm going to keep that the same. So using this formula here, speed when you strike the ground, and then, so I need to take the square root. Taking the square root, then the velocity is square root of 2 times the acceleration on Earth. That's about 10 meter per second squared.
times the distance is, or x minus x naught, that's 1 meter, square root it. And when you work out the units, you will see that you get meter squared per second squared, square root it, so you end up with a meter per second, which is the unit you want to get for velocity. So I need to work out these numbers here. 2 times 10 times 1 square root it, so square root of 20. I don't think I can do that in my head, so let me do that on this fancy graphing calculator. Well, scientific calculator. 20 square root it. 4.47. So that's not the answer, but that's step towards the answer. So speed when I strike the ground is 4.47 meters per second. And what we are claiming is that that's a safe speed to strike the ground with, whether you are on Earth or whether you are on Moon. So to find the height that you can safely jump down from, you say, all right, so this is going to be my final speed as I strike the ground on the Moon. Now let's see what my starting height was. So I go back to this equation here. Let me just write that out. Writing that out, I get v squared is equal to, or I guess, sorry, let me erase some of this. Actually, I think I want to go back to this equation here, which simplify the bits that are still simple. V squared is equal to 2 times acceleration times the delta x. So I have the v, so let's just plug it in, square it. Oh, then I'm gonna get 20 meter squared per second squared. That's what we had to start out with before square root. So we say that's equal to 2 times the acceleration is now going to be a sixth that of the Earth. So I say, all right, 10 divided by 6 meter per second squared, and then times delta x. So this is the equation where you can solve for delta x from. So so to do that, you just take all this number here and divide both sides by that number. So actually, let me work out the number on my calculator so that I have it ready to refer to. So that number is 2 times 10, so 20, divided by 6. So, okay, 3.33. So that number is 3.33 meter per second squared. So dividing 20 by that number will give you delta x. So let me do that. 20 divided by 3.333. I'm keeping a couple more digits. So 6. All right. So getting delta x, I get delta x is equal to 6 meters. So that's 6 times 1 meter height. So that should be the answer. Let's see. So you can jump from 6 times the height without risking injury. And the system says yes. And there are other ways to get to this answer more quickly. And I think the hint tries to walk you through that reasoning. It's conceptually a little bit more, there's more information to take in. But a kind of a technique, you can have to bypass the conceptual thing that you could work through conceptually. So you plug in the numbers and the numerical result gives you a guidance that's sometimes easier than working through the concept.